Okay, so good evening, everyone. So today we will continue with the question paper of BSTAT Entrance 2020 that we are discussing. So we had already previously discussed seven of the eight questions. So we are just left with the last one. So question number eight. So this is BSTAT 2020. So the question was, suppose, so they define something called an alternating sequence from a set of, so there is a set of n numbers, 1, 2, 3, 4 up to n, and a sequence A1, I mean a finite sequence A1, A2, A3 up to AK is called alternating. It's called alternating if A1 is less than A2, A2 is greater than A3, and A3 is less than A4, or if A1 is greater than A2, less than A3, greater than A4, and so on. So in either case, we can represent the number pictorially as a zigzag pattern of sequence of numbers. So these are what called alternating sequences. So they are up till k. The sign in the that will be decided by whether k is odd or even. So I'm not putting it here. So we have to. So for the set 1, 2, 3 up to 20, we have to find number of alternating sequences of order k, like where k is 5, so of order 5. So a1, a2, a3, a4, a5. Either this will be the relative order or this. So how to find all the number of such sequences? So 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 like 20C5, how much is that? Yeah, don't need to calculate. It's a pretty big number. So obviously you can't hand check all those sequences. So you have to devise some kind of method, some counting algorithm to count all such numbers. So the way to start is to use recursion. So let us define. Okay, first let us simplify the problem and try to solve a much simpler case of the problem. So suppose we have 1, 2, 3, 4 up till say n. So this is our set S. And now let's say that you only want the number of alternating sequence of size exactly n. So let un number of alternating sequence of size n. Okay, not just alternating. So starting with a1 less than a2. Okay, so here we are fixing the way our alternating sequence can start. So we are only allowing this one. and not this one. So the number of all such sequences is what we were assigning to un, so that the length has to be n and all the sequence terms have to be from the set S1 through n. Okay, so now let's see if we can find an expression for un in terms of the smaller ui's, like un minus 1 and un minus 2. So first observe that uh, the total number of alternating sequence, that is including this, okay, let us call this uh, the rising edge alternating sequence. So rising edge. Since the first two number, it has a rising edge. Let us call this falling edge alternating sequence. So UN is the number of rising edge alternating sequence, and you see we have a natural bijection between the two. Suppose we have a rising alternating sequence like this, then we can just take the complement. So, suppose this is the one level, right? The one level, and this is the n level. So n. So all the numbers from 1 through n. So this here is the 1, and this here is the n. So heights here represent the numbers. So this is the complement. So as you can see, the complement is a so if you flip it over, it will be like this, then small one, larger one, another small one, another way larger, small one, and the largest. So you see this is now a falling edge sequence from the same set 1 through n. Right. So here we get a bijection from UNs to like, so from this was a rising edge sequence to a falling edge sequence by inverting or taking the complement. So this operation is mathematically, so we have a sequence A1 up till AN. This is a rising edge alternating sequence. We are applying some bijection, suppose pi of this tuple, let's call it A. We're getting n plus uh, n minus 1 minus A1 up till n minus 1 minus AN. So we are subtracting each of the terms from n minus 1. So, so that's mapping 1 to just a minute, is it okay? No, sorry, this should be n plus 1, since 1 should be mapped to n. So n minus 1 minus 1, so n plus 1 minus 1 is n. And similarly, n is mapped to n plus 1 minus n 1. Right, so this manages complementing the terms of this. So the number of rising edge sequences is equal to the number of leading edge, sorry, falling edge sequences since they have a bijection. So our answer is obviously 2un, where the total number of alternating sequence is equals to twice the number of rising edge alternating sequences. So that's the first identity. Uh, Now let's try to break down un. So so un has, okay, instead of trying to break down un, let's try to break down 2un. So 2un is the total number of alternating sequences of size n from the set 1 through n. So either it can start like this with the falling edge, or it can start with the rising edge. So suppose uh, okay, so so suppose we arbitrarily break the sequence at some point k. Okay, not arbitrarily, like with a condition that the point at which we break it must have, the neighbors must be less than that. So this is ak. This is this is ak. This is ak plus one. This is ak minus one. Condition is ak minus one has to be less than ak, and ak has to be greater than ak plus one. So suppose we break the sequence at such a k, then we get two child sequences, one like this and the other like, and a point ak. Okay, so these are the two sequences. So those are the edges that I just snapped. So this has length k minus one, and this has length n minus k. So total we had a sequence of length n. So sequence of length n is basically two sequences plus a number ak. And this sequence, the first sequence of length k minus one, since we have put that condition on where to snap the sequence. So if k is odd, so if k is odd, that implies, so take any odd number for example. So this is an odd number, 3. So you see, so that sequence, the child sequence on the left is a falling edge one. So for k odd, we get a falling edge sequence of length k minus 1 on the left. So what is the number of such sequences? We know both of the falling edge and rising edge sequences of size k minus 1 are exactly uk minus 1. And similarly, if k is even, then also we have a rising edge. So 1, 2, 3, 4. So that was k here. This is k. Yeah, so we have a falling edge sequence. Right. So That is also uk minus 1. This is rising edge, and this is falling edge. But uh, in either case, we have the right child sequence, a falling edge one, right? So this is always a falling edge one. So that has a size of n minus k, right? So so 2uk, so 2un, sorry, the total number of alternating sequences of size n uh, can be broken down in the number of ways we can pick that ak. So suppose we pick the maximum of all numbers, that is n, as ak, right? Since we always want this condition to be valid, so it will be easier for us to ensure it if we pick ak to be the maximum. So we have the maximum n. So we want to pick where to put this n, right? So we can put n here, we can put n here, and here, and here, and everywhere, right? So k equals to 1 corresponds to putting the maximum value n at the first place. K equals to n corresponds to putting n here, the last one. So after putting n, suppose we have placed n somewhere. So at the position k, we have put n. Now we have to fill these ones with with k minus 1 numbers. So we pick them up from the remaining n minus 1 numbers in n minus 1 k minus 1 ways. And here we automatically get k numbers to put into. So now these k minus 1 numbers, so how many ways can we make so depending on k here, we will somehow want to make so we'll decide whether to make a rising edge sequence or a falling edge sequence, depending on the parity of k. Suppose k is odd. In that case, we need a rising edge sequence. The number of such rising edge sequence is again u k minus 1 and times. So the number of ways you can place these n minus k numbers is you will always make a falling edge sequence out of them, right? A falling edge sequence. So that is also u n minus k. So that's how we get this recursion relation. So we don't even need to solve this or don't even need a closed form, since we just need to find u5 somehow. So to find u5, so let's check a few base cases. So what is u0? So u0 is the number of alternating sequence when the set is empty. There is no sequence yet. So this is a bad base case. Let's try for u1 directly. So u1, we obviously have only one sequence. For u2, we have so 1 2 and 2 1. These are both alternating sequences, right? So u2 is 2. So using that, if we place n equals to 3, so substituting n equals to 3 in this equation, we get twice u3 equals k runs from 1 through 3 2ck uk minus 1 u U3 minus k, that is 2c1 u0 u2 plus 2c2 u1 and u1 plus 2c3 u2 u0. Right, so this already goes to 0 since 2c3 is 0. This equals 2u0 u2 plus u1 squared. Now to find, so we have to first find the value of u0, for which we can use this equation. This is 1c1 u1, sorry, u0 and u1. So u0 times u1 is 1. So this is k minus 1. Right. So 1c1 minus 1 is 1c0. And uk minus 1 is u0 and u2 minus 1 is u1. This 1c1 u. So u1 u2 minus 2 is again u0. Okay, so u1 is already 1. So 2u0 is it 2u0? 2u0 u1 is 2u2. So that gives u0 is 2. Something is wrong. Did I find the value of u2 correctly? So with two numbers, 1 and 2. Oh, sorry. So how we define u2 as the number of rising edge alternating sequences. So out of 1, 2 and 2, 1, only 1, 2 is rising edge, 2, 1 is falling edge. So u2 is actually 1, not 2. Sorry for that mistake. Yeah, so now it's okay. So u2 is equals to u0. That implies u0 is also 1. Right. So here we can now write it once more since 2c0 u0 u2 2c1 u1 u1 2c2 u2 u0. This is 1 times u2 is 1, u1 square is 1. This is also 1. No, so this is 2 and this is 1. So we get 4. So 2u3 is 4. So u3 is 2. Therefore, substituting equals to 4, we get 4c0 u0 u3, 4c0, 3c0 u0 u3 plus 3c1 u1 u2 plus 3c2 u2 u1 plus 3c3 u3 u0. That's 2 plus 3 times 1 plus 3 times 1 plus 1 times 2. So 6 plus 4, 10. So u4 is 5. Similarly, we get u5 equals so 5 plus which was 2, right? So 4 twos are 8 plus 6 plus 8 plus 5. So u5 is 8 plus 8, 16, 16 plus 6, 22 plus 10, 32. 32 by 2, that's 16. So u5 is 16. So now what is u5? u5 is the number of rising edge alternating sequences of size 5 from the set 1, 2, 3, 4 up to 5. Like this is not necessarily this set 1, 2, 3, 4 up to 5. It can be any set x1, x2, x3 up to x5 such that they are strictly increasing order. So we can just from the set 1, 2, 3 up to 20, we can pick 5 of them, like any randomly 5 of them, and then make a alternating sequences of size 5. So times twice u5 since we have to count them twice for leading and for falling and rising edge. So that's 32 times 20 c5. So must be some huge number. So let's look into it. 20 c5 is 15504. So that times 32 we get 496128. So that's the final answer. So this was by far the most hardest problem of 2020 ISI entrance. Anyone? Any doubts? So let me tell you how I solved it during the exam. So I just got till this step that somehow the number of so the number of rising edge and falling edge sequences are equal. So if I'm able to find the number of rising edge ones, then that should be enough. And I also got this step that uh, the numbers are not important. Just the ordering is important. So you can just consider the first 5 numbers 1, 2, 3, 4, 5, and total number of permutations with these five numbers is 120, right? So you can explicitly write out all those 120 numbers and cancel those which are not alternating. And then you get the u value of u5. That's 32. So it's not a very difficult task. Given 15 minutes, you can do it. And that's what I did. I don't know how much I got for that. So shouldn't be wrong actually. Okay, so now let's discuss about Ramsey numbers. Okay, so I don't remember if I talked about Ramsey numbers back in my PHP classes, P general principles. So it's very related. So this is mostly described in terms of graphs. Okay, so let me introduce it in terms of graphs. So suppose you have a complete graph of order n. This is a regular hexagon. Uh, so this is K6, a complete graph of order 6. So all possible undirected edges between any two vertices are drawn. Now suppose you color the edges in two colors. So then, so if Kn is colored in two colors, then for all n greater than RST, that is the Ramsey number ST. If n is greater than RST, then either there is a clique of size S or a independent set of size T. So if you color this K6 graph with two colors, then either there will be a K3 subgraph that is monochromatic, or there will be a K3 subgraph that is monochromatic of the other color. This is because R33 is 6. So that's what the friendship problem tells us. That if you have any six, if you pick any six random uh, students, then either three of them know each other or three of them don't know each other. So that is if you color them in two colors. there will always be a monochromatic triangle. A triangle is a complete graph of all three, right? So there will be a K3 of color red or K3 of color blue, no matter how you color those edges. So for a quick proof, so obviously if K R33 is greater than some P, then anything greater than P will always be, or what should I say? Yeah. So if you find like if you color Kn in all possible ways possible, and each of them you are certain that there is there is a subgraph of one color of size ks or a subgraph of the other color of size kt for that particular n, then you are sure that rst is smaller than that number n, right? So then you are also sure that for anything larger than n dash, rst will always hold. I mean, will always keep on finding ks and kt of one color or the other, since like you have this graph, right? Kn colored, and now we have some extra edges. Just randomly color the remaining edges. Okay, so yeah, so now let's move on to the proof of R33. Why is it 6? So first, let's show it's not 5, right? So it's greater than 5. Why? So if we have a pentagon, so I'm gonna color a pentagon, a complete graph of size 5, that is this thing, K5, with two colors like this. As you can see, we have colored K5 in such a way that there is the monochromatic triangle. Oh, sorry, there is a one, right? So then change this to green and this one back to orange. So now it's okay, right? No monochromatic triangle anywhere. So that shows our 3 is greater than 5. Now we will show that our 3 is less than 6. So how to show that? So think of some vertex. Okay, so let's consider the graph K6. So 1, 2, 3, 4, 5. So let's pick a vertex U. All the edges from U going to the remaining 5 vertices must be one of the two colors, orange and green, right? So with pigeonhole principle, there will be a color which will color uh, at like at least 3 edges of these 5 edges, at least 3 of these 5 edges. So without loss of generality, let us consider the first 3 edges to be orange, Orange is the first color, the remaining two be green. So now out of these three edges, the three vertices which are connected by an orange edge, look at the triangle that they form. Now if any of these edges are orange, then we will get a triangle like this. Since that can't we can't let that happen, so we have to color each of these edges with a green edge, and that will make a triangle again of color green. So in either ways, you can't avoid a green triangle or an orange triangle. So there will always be monochromatic triangle in K6 when colored with two colors. So that shows R33 is less than or equals to 6. So from these two, we can imply R33 is exactly 6. Okay. A much simpler result is R1K or 1N anything. So R1N, can anyone identify what is R1N? So what does it tell us? Either there will be a single vertex, or there will be n vertices. Sorry, or there will be n edges of the other color. So what is 1n? So take any complete graph of orders n, kn suppose. So if you just draw one edge, so a single edge is actually a complete graph of size 2, right? So what is k1? K1 is just a single vertex. So k1 is always true. Like every time you draw a non-null graph, it will always have a vertex, and that will imply that it has size 1, right? So R1n is actually 1, right? So anything more than one size graph will always have uh, what do you say, a vertex which knows which knows itself. Okay, so let's move on to a more interesting case, R2n. So now here we need to find either an edge of one color, say red, so orange, that is K2, or uh, there is Kn, a complete graph of order n. Okay. So how can we ensure both either one of them must happen? So we can just take the complete graph of order n. So any graph of order n with n vertices, what can happen? Either you color all the. Okay, so for simplicity, let me consider K4. So how will you color the edges? Either you will color all the edges one color, that will force that then there that is a green K4. So then you satisfy the second condition, or you don't color one of the edges green. Suppose you don't color this diagonal green, this color is orange. Then you got an orange edge that is an orange K2 to satisfy the first property. So that shows R2n is also n. So that's how we got R1n and R2n. Similarly, we can derive much interesting inequalities and upper bounds for MC numbers. Like RST is less than or equals to RS minus 1t and RTS minus 1. So RST minus 1. So how to show this? How to prove this inequality? So, so think about it for a few minutes. Like, obviously, we will take a let this right hand side be not n, other number n. So rs minus 1t and rst minus 1, let that be m. So so let's take a complete graph of size m. Yeah, so we have a complete graph of size m. Now pick any vertex, v or u. So how many uh, how many vertices are this vertex connected to? Since this is a complete graph, it's connected to all the remaining vertices. So the number of remaining vertices is m minus 1. So it's connected to m minus 1 vertices, right? So out of these uh, outgoing m minus 1 edges by PHP, there will be, so what is m minus 1? M minus 1 is rs minus 1t plus rst minus 1 minus 1. So either there will be uh, rs minus 1t of some color of one color. Suppose the two colors are red and blue. Then either rs minus 1 comma t be of red colors and the rest all blue, or rst minus 1 is of blue color and the rest all red. So at least rs minus 1t are of the same of one color, right? So pick all those vertices which are connected by a red edge. Since its size is greater than or equals to rs minus 1t, we will get a clique of, so we will either get a clique of size s minus 1, that is a complete graph of one color, of color, say suppose red, of size s minus 1. If we have got a size s minus 1 red graph, then we can just include the vertex u to that graph. So we got so s minus 1 union u. So this graph is of size s, since s minus 1 plus 1 is s. So this graph is of one color red. and it's also of size S. So we found a red graph, a red complete subgraph of size S. Similarly, if it had S, it had a subgraph of size T, which is color blue, then obviously that itself satisfies our condition that we need either a red graph of size S or a blue graph of size T. So here we got a blue graph of size T. In the other case, suppose we had got, so suppose uh, of those m minus 1 edges, only rs t minus 1, or the second number, meaning second many edges are blue. So let's consider a set of all those edges, all those vertices which are connected to you by a blue edge. So since that number is greater than or equals to st minus 1, so either it has a subgraph of a complete subgraph of size s which are red, so then we are done, or we have a complete subgraph of size t minus n which are blue. And then we can include u in that to get a size t blue subgraph. That proves that rst is less than or equals to rs minus 1t and rst minus 1. Okay. So that's it. Now the next inequality is, so the next identity says rst is less than or equals to uh, n plus, sorry, s plus t minus 2 by s minus 1. So how to show this? Pretty easy, just use the last result. So we know rst is less than rs minus 1t plus rst minus 1. And now let us use induction, right? So, okay, so what are our base cases? So base cases are, okay, I guess I have not proved an important identity before it. It's pretty trivial, just for your knowledge. We have to show first that RST and RTS are same. So that's pretty obvious. We can just swap the colorings. So suppose you have colored the graph with red and blue color for which RST holds, then we can just we can replace the color red with blue and color blue with red to get RTS. So in general, RST is equal to RTS. Okay, so now we know for the base case is uh, it's a 1n. So 1n is, or put 2n. So 2n is less than r1n plus rn1. or actually don't think this works for s and t to be all less than 2, I guess. Okay. So base case, so let me prove it formally. So proof by induction. Base case s equals t equals 2. So R22 is less than or equals to R12 plus R21. R22 is uh, so what is R22? Mm, yeah, we know 2n is n, so R22 is 2. Similarly, R12 is 1 and R12 is 1. So 2 is basically equals to 2, so 2 is less than or equals to 2. So base case holds. Now we have the induction hypothesis stating, let's assume for the sake of sorry, I mean, assume it's true for all s comma t in 1 2 up till n. So we need to show it. Need to show for n plus 1. What is for n plus 1? So R since this is a two-dimensional case, let's separately assume this. So true for all s in 1 2 up till s minus 1 and t in 1 2 up till t minus 1. Okay. I guess that would be difficult then. So okay, so let's assume it's true for all rs in this set x, not rs, st in this set xy, such that x plus y is less than or equals to s plus t. This is capital X and capital T, different from these s and t. So now let's see if we can show it for capital S and capital T. So now by the previous result, we know RST is less than RS minus 1t plus RS t minus 1. And from the induction hypothesis, we know these again are less than S minus 1 plus t minus 1. So t minus 2, uh, S minus 1 minus 1 plus S minus, S plus t minus 1 minus 2, C S minus 1. Okay, so that's S plus t minus 3 C S minus 2 plus S plus t minus 3 C S minus 1. So now we can use Pascal's identity. Pascal's identity. So it's basically derived from that Pascal's triangle, if you remember. So that triangle started from 1. We had 1 1 here. We had 2 1 1. This is 3. This is 3. This is 1 1. this 4, this is 6, this is 4, this is 1, sorry, and so on. So each entry in the lower column are the sum of the neighboring entries from the previous one. So that's why we have Pascal's identity is given by NCR equals to minus 1 CR minus 1 plus n minus 1 CR. Okay. So with that, we know that RST is less than. So this is n minus 1, right? And this is n minus, this is r minus 1, this is r. So we have the sum is equal to n, that is s plus t minus 3 plus 1, so minus 2 CR, that is s minus 1. So now with the induction hypothesis, we have shown this is exactly the statement for RST. So sorry, I changed that t to small. Okay. So we have proved this. Now the last important identity is Ramsey is a lower bound. So we need a lower bound, right? So we got a pretty good upper bound. I mean two upper bounds. Now we are looking for a lower bound. So show that uh, r rk by 2 is this one equals to rkk is then equals to 4k. This I guess equality doesn't hold you. So this was established by Paul Erdos. I will just prove this part, the lower bound. We will use something, a trick in probability to find that lower bound, to calculate it. I will give you guys 5 minutes to think about it first. Sorry, I had some technical issues due to which I couldn't share my screen. Okay, so let's move on with the proof. So now suppose we like if we take a kn graph, say suppose a kn graph with n vertices, complete graph, right? So we have nc too many edges to color, and we randomly color the edges red or blue with two colors. Then what is the probability that we might find a kx subgraph which is all the same colors? So to find that probability, we simplify it like this. So what do we want? We want a kk subgraph, so a complete graph of size k. How many edges does that have? Kc k many edges. So all those have to be colored in the same color. So either all the edges are colored in red. So since each edge can be colored in red with probability exactly half, since we are unbiased in our coloring. So KCK many edges can be colored in red with the probability of half power KC2. Right. And since red is not important, we can color it also in blue. So we have to add another half power KC2. So that is the probability of finding a KK. So either we have to color the any K. This has to be multiplied with this has to be multiplied with NCK. So to so to find a K by KC, like sorry, not a case. To find a complete graph of size K, we just pick any K vertices and color all the edges in between them with either red or with blue. Right. So this probability is strictly not equal to, since it's this probability is uh, just a minute. Yeah, this probability is way less than it, since we are ignoring the other intersection terms. Okay, this is less than or equals to NCK 2 power 1 minus KC2. That is n factorial by n minus k factorial times k factorial. So it's 2 by, or just a minute, so it's so if you simplify, it's k into k minus 1 by 2. So 1 minus k into k minus 1 by 2 is 2 minus k squared plus k. That is so it's 1 minus, sorry, 1 plus k by 2 minus k squared by 2. So it's 1 plus k by 2 and minus k squared by 2 I'm taking in the denominator. So it's plus k squared by 2. Now, so now observe that n factorial by n minus k factorial is n into n minus 1 into till n minus k plus 1. That is also sometimes written as n power k falling factorial. Okay, so don't call it, you don't use this notation much, but it does exist. So now each of these factors are less than or equal to n. So their product is less than or equal to, so n power k. There are k many of them, right? So this thing here is less than or equal to k in power k. That implies n power, the whole thing is less than or equals to n power k by k factorial times 2 power 1 plus k by 2 power k squared by 2. Okay, now, okay, so now let's substitute. Uh, so let's put n equals to 2 power k by 2 now. Let's see what happens. So if we put 2 power k by 2, so put in the above equation. So we get this probability of finding a complete subgraph of size k is less than or equals to 2 power k by 2 k squared by 2. That power whole power k, and let me not jump steps. So this is 2 power k squared by 2, and this is k factorial and 1 plus k by 2 by 2 power k squared by 2. K squared by 2 cancels out, and now we are left with k factorial. Now you see, in the denominator we have 1 into 2 into 3 into up till k. And then numerator we have 2 times 2 times only half many 2's, right? Almost half many. So this thing is obviously strictly less than 1. If k is greater than or equals to 3. Right. So what did we show? We showed that for n, let's write the conclusion here. Hence, for n uh, less than or equal to 2 power k by 2, the probability of finding k k or a clique of size, this complete subgraph of one color is called a clique. So a clique of size k is less than 1, less than 1. That shows there are some cases, like for all possible graphs of size n, where n is equals to when n is less than 2 power k by 2, there are some graphs where uh, sorry, not less than, it's exactly equal. So there are some graphs where this condition, this Ramsey condition doesn't hold, that there are some graphs where we may not find any clique of size k. Right, that's why the probability is not equal to 1. As if always you had found a graph of size, a subgraph of size k, then that probability should have been exactly 1. But we have found that 1 is a non-reachable upper bound. This is a strict inequality. Observe that. Okay. So 2 power k by 2 is strictly less than our kk. And now for the upper bound. So for the upper bound, for that we need to derive this inequality, that rkk is less than r2k minus 4 k minus k minus 2. Actually, this proof is pretty cumbersome, so I'm just leaving out, leaving it out. Just remember the result and not this. Don't think the probabilistic method works here. Okay, so now let's move on to one example. So, example. So try this one. So show that R44, the Ramsey number of order 4, comma 4, is exactly equals to 80. If you, for a quick check, if we use that upper bound, first one, that is s minus tt and st minus 1, we use that, we get twice R34. So what is twice R34? R34 can be further broken down into R23 plus R33. Right, and R23 is just 3, and R33 is 6. So 6 plus 3 is 9, 8 to 9 twos are 18. So we got 18 as a clear upper bound. Now if you use just the previous this upper bound, let's see what we get. So 2k minus 4ck minus 2. 2k minus 4ck minus 2. That's 4c2. 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 I don't think this. Okay, let's use this upper bound. 4 power k. It's 4 power 4. I guess those upper bounds have some more restricting conditions that's not valid for this problem. Okay. Okay, so now as we have proved it's less than or equal to 18, we have to somehow show that it's strictly larger than 17, or it's not 17. So we have to find a counterexample for 17 or construct one somehow. How are you going to do that? So for that we will use something called, no, not necessarily. Okay, let's do it normally. So we need to construct a graph, or we need to generate a coloring of the complete graph of order 17, such that there doesn't exist any K4 graphs of either subgraphs of either color. K4 looks like this, a square with all its diagonals. or a quadrilateral with all its triangles. So let's consider the residue class of 17, mod 17. So it has, sorry, so it has these 17 elements. So this is Z17. So we are numbering the vertices from 0, 1 up till 16. Right. So now between any two vertex, U and V, the color of that edge, let's color it with mod Vi minus or mod V minus U. Okay. So this color is modulo 17. Oh, sorry, you have to color it with only two colors, right? Okay, so then uh, so we have to do this thing. So a quadratic residue. So what is a quadratic residue? So quadratic residue. So all those remainders modulo some number, some prime p, say suppose 5, a perfect square gives. That is, so the residue class of 5 contains 1, 2, 3, 4. If you square them out, let's see what remainders they give. So 0 gives 0, 1 gives 1, 2 gives 4, 3 gives 9, that is also 4, 4 also gives 16, that is also 1. So we find that the quadratic residues of 5 are 0, 1, and 4. Similarly, we can find that quadratic residues modulo 3 are 0 and 1. And similarly, for 8, for 4, it is 0, 1, and minus 1. This is mod 4, this is mod 10, this is mod 5. Similarly, the quadratic residue is modulo 7. Let that set be 0 and 1 are obviously there. So some set, right? So let's call it Q17. So Q17 is a subset of Z17. The vertices that correspond, no. Okay, so yeah, so these numbers S V mod modulo 17. This number is in between 0 and 16, right? But so they are in Z17, but they may not be in Q17. We will color the edge accordingly, red and blue, if it's in Z17, in Q17 or not. So color it in red. So color equals to red if U minus V is in Q17. Otherwise, color it blue. So that's the color scheme we have developed. Okay. So now let's see what happens with the graph. So suppose after that coloring we get a group of four vertices which have the same color. Say suppose blue, so, or red. Let me draw it in red. So red. So without loss of generality, let's assume this is 0, this is x, this is y, and this is z. Okay. So this this is x minus y, this is y minus. Let's assume this inequality, this ordering between them. So that is this is z minus y, and this is also z. This is, we don't know the color, so I'm drawing it in black. So this is z minus x. Similarly for this edge, this is y. And now, since we want to, let's assume that, uh, yeah, let's assume our, sorry, let's assume our 4 is less than or equal to 17. Since we want to prove it's greater than, this is greater than 17, we can assume it's less than or equal to 17 and then show a contradiction. So assuming that we've generated a color scheme, so if it's anyways true, then we should always get a monochromatic K4, right? And for that, we also will have a C4 monochromatic. That is this, like this is, suppose this is that quadrilateral which is monochromatic. So that means x, y, z, x minus y, y minus, sorry, this is not x minus, this is y minus x. So y minus x, z minus y, z minus x, and y, and yeah, these 1, 2, 3, 4, 5, 6. These six numbers have to be quadratic residues modulo 17. So they have to be in Q17, since they are colored in red. So since we have assumed like the zero separately, so x and y and z, none of them are zero. So this is a property of residue class of prime modular prime number. That the residue class, suppose a1, a2 up to ak are, sorry, up to ap are the 0, 1, 2 up to p minus 1 modulo. So this is zp, the residue class modulo p. Then each of the numbers have an inverse, that is, when multiplied to itself, it gives rise to 1 modulo p. Right, if p is prime, then that happens. Take, for example, this thing, the residue class modulo 5. So what is the inverse of 3? We know 3 times, uh, yeah, 3 times 2 is 6. 6 is congruent to 1 modulo 5. So 2 is considered the inverse of 3 and so on. 3 is considered the inverse of 2. Okay, so all these numbers have a multiplicative inverse modulo 17, since 17 is a prime number. So if we say that capital Y is Y times A inverse, and capital Z is Z times, I mean not A inverse, X inverse. So X inverse is the inverse of X modulo 17. And look at this set. 1, capital Y, capital Z, capital 1 minus capital Y, 1 minus capital Z, and Y minus Z. So what's the issue in here? The thing is, this is also a quadratic residue, this set. So one we already know is a quadratic residue. So y was a quadratic residue, and if we multiply y times x inverse with itself, no. So we know y is a quadratic residue. Suppose k squared is congruent to y modulo 17. Okay. Now take the number kx. Just a minute. So kx times kx is k squared. Basically, the inverse of any quadratic residue is also a quadratic residue. So that shows z and y are quadratic residues. And when we subtract y from 1 minus from 1, then we get another quadratic residue. And since the quadratic residue, the set of a quadratic residue mod 17 is, we can find them, right? Like you can check it's just 1, 2, 4, like including 0. So 0, 1, 2, 4, 8, 9, 13, 15, and 16. And you will just see that this we can't pick x and y and z here such that we get this set to be in a subset of Q17. And that's just gives us the contradiction that we're looking for. So R44 can't be R44 can't be equals to 17. And since I've already shown that R44 is less than or equals to 18, so R44 has to be equal to 18. Okay. So okay, so now let me should I give them assignment? Or let me end the class here. Okay. So bye then everyone. We will meet next week. Good night. I'm ending the class here. You can leave.